I all hope all are fine at home. Now we shall see the second chapter of our module 1, that is steam nozzles. You know, the steam nozzle is a varying area cross section where the heat energy of steam is converted to kinetic energy. That is, the steam nozzle is placed before a steam turbine. So nozzle converts the available energy to kinetic energy, and the steam with high kinetic energy, high velocity is given to the turbine where it produces the power. So basically there are two types of nozzles, a convergent nozzle, a conical cross section, and a convergent divergent nozzle. The section with minimum area is called as throat of the nozzle. So it is a flow device, and we can apply the fundamental equation, steady flow energy equation, SFE. So H1 plus C1 square by 2 plus Z1 plus dq by dm is 2 plus C2 square by 2 Z2 dwx by dm. One is the inlet of the nozzle, 2 is the exit of the nozzle. And by neglecting the potential difference, Z1 equal to Z2, and by assuming the flow through the nozzle as adiabatic, dq by dm equal to 0. And in nozzle, only the energy transformation takes place. There is no external energy transfer. Only one kind of energy is converted to other kind, transfer to surroundings. This wx is basically the external work. So as there is no energy transfer, external energy transfer, this wx is 0. Wx is basically the shaft work. Here there is no shaft. So by taking those values as 0, and by putting z1 equal to z2, the equation reduced to h1 plus c1 square by 2 equal to h2 plus c2 square by 2. So that is the fundamental equation for a nozzle. And when substituting here, your H1 and H2 should be in joule per kilogram. Basically, we are taking values from steam table or modular chart, that the unit is kilojoule per kilogram, and by substituting here, you convert to joule per kilogram. And this C1 is the inlet velocity, and the inlet velocity will be very small when considering the exit velocity C2. So in some cases you can neglect it. So by neglecting inlet velocity C1, by putting C1 equal to 0, this equation becomes H1 equal to H2 plus C2 square by 2. C2 square is 2 times H1 minus H2. And you substitute H1, H2 in kilojoule per kilogram, and for converting that kilojoule to joule, you multiply that by the equation by 1000. So this C2 is root 2000 H1 minus H2, root 2000 is 44.72, so C2 is 44.72 into root of H1 minus H2. So we got two equations, both are same. The first one is useful when C1 is given, and the second one is useful when C1 is negligible. Now we shall consider a convergent divergent nozzle. One is inlet, 2 is throat, 3 is exit. The general expression for the expansion through the nozzle is PV raised to n is a constant, where n is the index of expansion. The value of n depends on the quality of incoming steam to the nozzle, and the incoming steam can be a superheated steam, dry saturated steam, or wet steam, and n is 1.3 for superheated steam, n is 1.135 for saturated steam. And for wet steam, the n depends on the value of x, where x is the Reynolds fraction. N is 1.035 plus 0.1 x. And there is one more important term, it is called as critical pressure ratio. Its derivation is very important, that we will do in class. Now the derivation is, that is a pressure ratio, the definition is, it's a pressure ratio between throat and inlet for the maximum discharge through the nozzle, and that is a constant, and depends on the value of n. P2 by P1 is 2 by n plus 1 the whole raised to n by n minus 1. And basically we are using a modular chart for solving the problems from steam nozzles. And the modular chart is the graphical representation of your steam tables, in which the specific enthalpy is plotted along y-axis and the specific entropy along x-axis. And you have a middle curve, that is the saturation curve, and the region below the saturation curve is wet region. You can see the red curves, that is constant Reynolds fraction curves, and in both regions you can see the pressure curve, the green curve, the temperature curve, the blue curve, and the region above the saturation curve is superheated region. Now the different losses in the nozzle. Basically, the final velocity is less than what we expected, that is less for a given pressure drop, and the reasons are the friction between nozzle surface and steam, the internal friction of steam, and different shock losses. So the basic reason is friction. And the effect of friction is, by considering friction, the flow becomes irreversible, so that the expansion is not isentropic, and the expansion will be happening with increase in entropy. Any effect of friction will increase entropy, so that will happen with increase of entropy. And by that the final enthalpy is more, means the by the effect of friction the steam is reheated. The heat involved by the effect of friction is transferred to steam, so that some part of water will be converted to vapor, so that the Janus fraction increases, the final Janus fraction is increased. So as it contains more amount of vapor, the specific volume is also increased. So we shall see with the help of a modular chart. So in HS diagram, 1, 2 is the ideal expansion, isentropic expansion. Entropy remains constant, S1 equal to S2. So there is a vertical line in your modular chart. And by the effect of friction, the entropy increases. So it is expanded to same end pressure. So in the same pressure curve, you are getting a point 2 dash, 2 shifted to 2 dash. That is the effect of friction. So 1, 2 dash is the actual expansion. And you take the enthalpy difference, H1 minus H2 for isentropic expansion, H1 minus H2 dash for actual expansion. H1 minus H2 dash is less. So a term called as nozzle efficiency. The lower value you put on the numerator, H1 minus H2 dash by H1 minus H2. And if it is a convergent divergent nozzle, the effect of friction is more evident in the divergent section. 1, 2 is the convergent section, 2, 3 is the divergent section. The convergent section is basically very small, its length is less. So the effect of friction is evident in divergent section, so that 2, 3 is not at all 2, 3 is isentropic, and it is not at all isentropic in the actual case, so that 3 is shifted to 3 dash. So 2, 3 is the ideal expansion in the divergent part, and 2, 3 dash is the actual expansion. And just note that there is no change in the convergent part. And the actual enthalpy drop is H1 minus S3 dash, and the isentropic enthalpy drop is H1 minus S3. So actual drop H1 minus S3 dash is less. So the lower value is on the numerator. So nozzle efficiency for a convergent divergent nozzle is H1 minus S3 by H1 minus S3 dash by H1 minus S3. And this increase in enthalpy, that is for a convergent nozzle, it is S2 dash minus S2, and for a convergent divergent nozzle, that is S3 dash minus S3. It is called as friction reheat. S2 dash minus S2, S3 dash minus S3. Now we will see some problems about